This is the 7th lecture in module 4. In this lecture, we will be discussing one of the speed control methods, that is rotor resistance control of induction motors. The next method of speed control is rotor resistance control. This is the equation for maximum torque developed in an induction motor. This equation we have discussed in lecture 2. And you can refer lecture 2 for more details. In this equation, we can see that the maximum torque capability of an induction motor is independent of rotor resistance. RS is the stator resistance, XS and XR dash are the stator and rotor reactances. So, rotor resistance is not in this equation. That means Tmax is independent of rotor resistance RR dash. Similarly, we have another equation, that is slip at which maximum torque occurs. That is SM. Slip at which maximum torque occurs. In this equation, we have a term RR dash. That means that slip at which maximum torque occurs is proportional to RR dash. That is slip or speed. Slip indicates the speed at which the rotor of the machine is rotating. So, slip or speed at which Tmax occurs depends on RR dash. That means we can control the speed of an induction motor by controlling the or varying the rotor resistance RR dash. Now we will discuss the performance of an induction motor with rotor resistance control. The figure shows the torque speed characteristics of an induction motor for different values of rotor resistance R dash. So for the first curve indicates the torque speed characteristics of the induction motor with smaller value or low value of rotor resistance. This curve shows the cara for a much higher value of rotor resistance. This curve, the third curve, shows the top speed cara with again a higher value of rotor resistance. So rotor resistance increases. So we can see that as rotor resistance increases, speed decreases. The y-axis we have plotted speed. So speed goes on decreasing. But we can see that for all the cases, for all the three cases, the maximum torque capability Tmax of the induction motor will remain the same for any value of rotor resistance, or in effect for any value of speed. The maximum torque capability of the machine will remain the same, and these dotted lines are shown in order to indicate the corresponding rotor current profiles for these three torque speed characteristics. So, as a conclusion, we can say that for a given low torque, the motor speed falls as the rotor resistance is increased. This is the key point for rotor resistance control. So, another thing is the no load speed, that is the speed when torque, x-axis torque is equal to 0. This is the no load speed. The no load speed remains unaffected by the variation of rotor resistance. So, no load speed will be the same for all the curves. So as rotor resistance increases, speed falls. Another thing is the efficiency of this induction motor. This equation is familiar to us. We have already discussed this equation. So efficiency is approximately equal to PM by PG. PM is the mechanical power developed, and PG is the air gap power of the machine. It is equal to 1 minus S. And the equation for rotor copper loss is 3 into IR dash square RR dash is equal to SPG. So when you implement rotor resistance control, the method is in order to connect an additional resistance, variable resistance in the rotor circuit. An external resistance will be connected to the rotor circuit in order to control the speed. So the rotor copper loss will be higher, much higher when you increase the value of rotor resistance. So the overall efficiency of the drive decreases as you increase the rotor resistance, since the copper loss increases. But the good thing is we are adding resistance externally, so the heating, the overheating of the machine will not happen, because the heating will be happening in the mainly happening in the resistance that is added externally. In the external resistance there will be heating. Let's discuss the advantages of um, rotor resistance control. The main advantage is that the motor torque capability remains unaltered even at low speeds. Even at very low speeds, we can see in the top speed Cara that the um, maximum torque capability remains the same at any value of speed. And the cost is very low. The cost of rotor resistance control of induction motor is very low compared to the variable frequency control. As we have discussed in the previous lecture, that variable frequency control is very much costlier as compared to other drives, even though it is having many other advantages. So this method is very cheap. So, because of the low cost and high torque capability at low speeds, rotor resistance control is employed in cranes and other intermittent load applications. It's a very popular method. The disadvantage we have already discussed. The low efficiency due to additional losses in the resistance connected in the rotor circuit. But as the losses mainly take place in the external resistor, they do not overheat the motor. Now let's see how the rotor resistance control of induction motor is practically implemented. This is done with the help of static rotor resistance control. In a conventional method of rotor resistance control, we will be using a rheostat. But rheostat is having moving parts, and it requires maintenance, frequent maintenance, and difficult to operate. But static rotor resistance control consists of a fixed resistance and a switch. That is a power electronic switch, static switch, which can be controlled easily. So the combination of the fixed resistance and the power electronic switch will be used to control the rotor resistance and thereby the speed of the motor. This is the circuit diagram. Here, this is a slip ring induction motor. Since the rotor resistance of a squirrel cage induction motor cannot be varied, it cannot be used for squirrel cage motors. Only this method is used only for wound rotor or slip ring induction motor. So this is the stator winding. Stator is given a three-phase AC supply, and this is the rotor. From the rotor, we are taking out the rotor terminals, and they are connected to a diode bridge rectifier. And at the output we have an inductance LD, which is connected to remove the ripples in the current, that is the DC link current ID. And these are the terminals A and B. The resistance across the terminals A and B will be controlled with the help of this combination of resistance and the switch. This is a power electronic switch. It may be a MOSFET or any kind of power electronic switch that can be controlled by controlling the gate signal. So by controlling the duty cycle, that is the duration for which the switch remains on, we can control the effective resistance across these two terminals. If the switch remains on for a long duration, the effective resistance will be less. That means if the switch is on, that means the resistance terminals of the A and B terminals are short circuited. That means the resistance is not included in the rotor circuit. If the switch is open, the resistance gets included in the rotor circuit. So by controlling the duty cycle of the switch, the effective resistance across A and B will be controlled. And this is the rotor phase current and phase voltage waveforms. Rotor phase current means the voltage induced in the rotor circuit, rotor induced EMF. and this is the waveform of rotor induced EMF, and this is the waveform of rotor current, and the magnitude of this current is ID. And these are the conclusions. The effective value of resistance across the terminals A and B, RAB, is varied by varying the duty ratio of transistor TR, which in turn varies the rotor circuit resistance. And the inductance LD is added to reduce the ripple and discontinuity in the DC link current ID. The ripple in current ID is neglected. Now let's see how to choose the value of duty cycle in order to get a particular value of rotor resistance. Then only we can control the speed of the motor. First, let's write the equation for energy absorbed by the resistance R during a period of operation of the switch. That is, period of operation of the switch means when the switch remains on and off. T on plus T off of the switch will give you T, period of operation of the switch. We are considering a particular period of operation, that is EAB is equal to ID. ID is the DC link current, ID square R into time for which the resistance comes into action. That is, resistance is included in the circuit. The resistance gets included in the circuit only when the switch is off. That is, only when the switch is off. That is, T minus T on will give you T off. So ID square R into T off is the energy absorbed by the resistance R. When the switch is on, the resistance will not be included in the circuit and it will not absorb any energy. Next, the average power absorbed by the resistance R during the period T is PAB. That is, equation of power is equal to energy divided by time. That is, PAB is equal to ID square R T minus T on divided by T. T is the operating time of the switch, period of operation period of the switch. But T on by T is equal to delta. Delta is the duty cycle of the switch. So in this equation, we have T minus T on by T. That is, this becomes 1 minus T on by T, or 1 minus delta. So PAB is equal to ID square R into 1 minus delta. That is the equation for power absorbed by the switch. So we can see power absorbed, power absorbed by the resistance. So we can see that the equation for power absorbed by any resistance is I square R. That means I d square into this term. This term gives the effective resistance of effective resistance across the terminals A and B that we have seen in the circuit. Hence, the effective value of resistance R across the terminals A and B, RAB, is equal to R into 1 minus delta. So we can say that in order to control the resistance across A and B, we have to vary the value of duty cycle delta. So we can control the speed of the motor by varying the value of delta. Now let's see what is the power consumed by the resistance. That is effective resistance RAB. The resistance across the terminals A and B is RAB, effective resistance. So what is the power consumed by this resistance? It is equal to PAB. PAB is the total power consumed. So here we are calculating the per phase values. So PAB is PAB divided by 3. It is ID square R into 1 minus delta divided by 3. Now we are going to substitute another term, that is ID. The RMS value of rotor phase current is given by IR dash, that is a rotor per phase rotor current. IR dash is equal to square root of 1 by pi integral 0 to 2 pi by 3, that is 120 degree, into ID square d omega t. This is this equation is written from the waveform that we have seen earlier. It is equal to root 2 by root 3 into id. So in this equation we can write id is equal to root 3 by root 2 into ir dash, and this is to be substituted here for id. So the per phase power consumed by resistance RAB is equal to, after substitution we will get the equation like this, that is 0.5 into R into 1 minus delta into IR dash square. So in this equation we can see that a power consumed by the resistance is equal to IR dash square, that is rotor current, into this term I square R. In the equation for I square R, I square into another term. So this term must be the resistance, effective resistance of that circuit. So per phase resistance is equal to 0.5 into R into 1 minus delta. This is the resistance of the external circuit connected. So the actual or total resistance of the rotor circuit will be equal to the actual rotor winding resistance plus this resistance. So the total rotor circuit resistance per phase is equal to RRT, RR total is equal to the actual value of rotor resistance or rotor winding resistance, which cannot be changed, plus the external resistance, the effective value of external resistance. These are all per phase values. So RRT can be varied from RR to RR plus 0.5 R. That is, if the value of delta is equal to 1, then the total rotor circuit resistance will be equal to RR. If delta is equal to 0, then RRT is equal to RR plus 0.5 R. So it can be varied from RR to RR plus 0.5 R as the delta is changed from 1 to 0. That's how we are controlling the speed of the induction motor by varying the rotor resistance. Next is the closed loop speed control with static rotor resistance control. The block diagram shows the same drive that we have discussed earlier and a closed loop control system. Here the actual speed of the motor is sensed using a speed sensor, that is omega m, and is compared with the speed command, that is a desired speed. Desired speed minus actual speed will give the error signal, which is given to speed controller, and the output of the speed controller is given to current limiter. So the current limiter will is designed such that it saturates at a constant value of current, which will give the maximum torque for the motor. So this helps to operate the motor with a very fast transient response during motoring as well as braking. And the output of the current limiter is the current command ID star, and it is compared with the actual current DC link current ID, and the error signal is given to the current controller. The output of the current controller is given to base drive. Base drive will generate the gating signal for the switch or transistor TR. The gating signal is delta star, and by controlling the gating signal or on and off time duration of the transistor, the effective resistance across these two terminals is controlled, thereby controlling the speed of the motor. Thank you.